recording. Okay, so started recording on the whole things. Okay, I need to talk about a bit of like chemical reactions of the organic compounds, and that's basically what I want to cover today. So when we're talking about chemical reactions, I need to put alcohol always in the middle like this. So I will share this screen, and you can have a look at the later too. So what I do for the this alcohol is I just divide that into the half like that. Okay. On the top of the grid, it is known as the production. The production of the alcohol. At the bottom would be use of the alcohols like this. And then we can think about how the alcohol can be produced and how be used in different chemical reaction forms. All right. Have you learned anything about how to produce the alcohol in school?
Not yet.
Yeah. So how do you make alcohol?
Uh, we haven't learned it yet.
Okay, you haven't learned it yet. Okay.
Yeah.
All right. The way we can make the alcohol is there are several methods to make an alcohol. One is that I use the blue for my functional group. I can use the alkene. So as you know, alkene is a double bonded structure, and I use alkenes to move it on to the alcohol. So you may just think about use of different colors. Hang on, I use this color here. Okay. Alkenes to alcohol like that. So in the purpose of that, this will be known as the hydration or the addition, the reaction. So I put there as equation one, and also known as hydration process. So equation one here like that. Okay. And then what I do, I will write it down all the chemical reaction that you need to know on the separate note. So I can share that notes later on once we finish the class today. So hydration of alkene. This is the type of an addition reaction. Okay, so when we have the alkene, so for example, I can have the structure look like this. Name of this, as you know, is an ethene. So what do we do basically is hydration process. We are adding some water, H2O, onto it. Then what happens to water is this is going to be separated into the hydrogen ion and the hydroxide ion. And basically it will be added on to this double bond. So the structure of that will look like this. That's okay. Goes like here. Because water is not strong enough to break the bonds of the double bonds of the ethenes or the alkanes, we need a bit of help of the concentrated H2S, oh, sorry, the diluted, that's concentrated, diluted H2SO4, which is sulfuric acid. So with the help of the sulfuric acid, it is working as a catalyst. It opens up the double bonds of so this directly opens up double bonds of the alkenes. Therefore, the water can be attached or just simply added to form this structure of the alcohol, which is known as ethanol produced like this. Okay, that's the first reaction with dehydration. And
Mm,
whenever we're adding something, just adding something without like it's a byproduct, and you see like there's nothing else produced but just the ethanol. The
yeah.
reaction is known as the addition reaction. But when we have the substitution, there'll be a byproduct produced. So
Oh,
that's the one reaction we need to know. Yep. So I
no,
just
no, I just said yeah.
okay, cool. Yeah, that's fine. I just write it down. We need to have diluted H2SO4. As you need to memorize all the catalysts working for like so each of the reactions. Okay, that's one reaction, but we can also going backwards from the alcohols to the alkenes like this. So I call that reaction as dehydration. Okay, so it's pretty simple. Like when we hydrating, adding the water into the alkene, that's known as the hydrations. We need the dilute H2SO4 for that. But when we like try to remove the water from the alcohol, it'll be known as dehydration. And it's fairly easy to remember too. The catalyst required for the dehydration process is concentrated H2SO4. So the way you can think about the difference between hydration and dehydration is when we're adding the water, we need extra water. Therefore, the acids become diluted as we add in extra water. But when we're dehydrating, we don't really need much water because we need to remove the water. Therefore, we need the concentrated H2SO4 forms. So writing this one down in the next page, showing you the two. Oh, so dehydration of the alcohol. It would look like this. We have the ethanol. And it doesn't really require anything else. We just need concentrated H2SO4. As a result of that, we're now getting the ethene back with a bit of like some water will be coming out as a result of these dehydration process. Okay, any questions for the hydration or dehydration of the alcohol?
No.
Good. All right. Another method that we can produce alcohol is we can start off from something that's known as haloalkane. So I just put the haloalkane in here. Haloalkane. So haloalkane is simply the alkane with the single bonded carbons with the one or two, basically just simply one the halogens attached. So example would be chloroethane. But from the haloalkane, we can move it on to the alcohols. We can actually produce the alcohol from haloalkane like this, and process known as reaction 3, known as this is known as substitution. Um, yeah, substitution. And for the substitution of, we have the OH minus. Okay, so let's have a look at the reaction 3, and from the alcohol, I showed the 3 and 4 in the same time. So from alcohols, we can also have, we're going back to the haloalkane process. That's a 4 known as the another substitution of the in that case of the halogens X or B. So how does it form? So let's write it down. The chemical reaction for substitution. Substitution of OH minus on the haloalkane. It would be look like this. So we have, assumed we have haloalkane, so one chloroalkane look like that. It could be bromo, it could be iodo, it doesn't really matter, but I just simply use the chloro because it's the most common like haloalkane we use. This, when this is reacting with, so we're actually adding some strong base, like a sodium hydroxide or the potassium hydroxide. We generally use the sodium hydroxide though. So when this is reacting, hydroxide is taking a place of the chloride. And then what it becomes to is it becoming like this. We have chloride is replaced by the hydroxide, becoming into ethanol again too, or just the alcohol in the functional group. And remainder would form the salt, NaCl, we produce too. So we get the some byproduct, and as you can see, like we have some byproduct, which is a sodium chloride is produced, the byproduct. Unlike the addition reaction we had on the top on the hydration process, which there is no byproduct produced, this is known as substitution reaction, as we get some byproduct produced. Does it make sense? Can you like spot the difference between substitution and addition reaction now?
Yeah. What would they do with the byproducts like after the?
Oh, it just stays there basically. Sodium chloride stays there. So you may just think like this is like an ethanol with having some salt in it.
Oh, okay.
So it's not a pure alcohol though. I mean, pure alcohol, like compared to the hydration, the alkene, which we get the pure alcohol, like ethanols only. Of course, there is some sulfuric acid left over too. But in terms of how to maximize yield or like purely on the increase the purity of that, that's something we're learning later on in module 8. Okay, so moving on to this, number 4, substitution of the X minus on the alcohol. So if you want to go backwards, so for example, if assume that we have ethanol again, the here like this. If you want to replace that, and we can add some HX life forms too. So for example, it could be like hydrochloric acid or like hydrobromide, even like hydroiodide, but acrylic acid is commonly generally used because it's known as the acid, is known as the acid. And this is placing the X is take a place of the OHs too. So X is the symbol for the halogen. It's good to remember that as well too. So we become substituting that with the X. So for example, chloride will be attached. But as a result of the substitution, we get the byproduct, which is the water will be coming out as well too. Okay, so that's a second method of producing the alcohol from the haloalkanes, or the going backward from the alcohol to the going back to the haloalkanes too. Okay, so generally there are two methods producing the alcohols. So I talked about alkenes and haloalkanes, which are provided here like this, which is good. Now, let's talk about a bit of like, then how to produce the haloalkanes. There are a few methods to producing haloalkanes. One method is we can use the alkane, just as pure alkane itself. And from here, we can make into haloalkane straight away, like this. Okay. The way we can do that is this is also known as the substitution reaction. So number 5, substitution. Our second method is we're going from alkane to the alkenes. Okay, and then alkane to the haloalkane method, like this. So that number 6 reaction is known as hydrogenation, which is different to the hydration process. And alkene to the haloalkane would be addition reaction 7. Addition. The reactions are like this, or like sometimes known as hydrohalogenations. So let's show. I show them what happens for each of the step of the alkanes to alkenes, the haloalkane structures. Need a new page. That's the question 5. So one of the reaction from alkane, so alkane to haloalkane, which is a substitution. The reaction of that. For this reaction, we need to have alkane. So let's draw the alkane structure, which is I can draw the 2 carbons with the hydrogens, so known as ethane. Now, unlike the ethane is kind of completed. We call this as kind of saturated carbons. The meaning of saturated is same terms we're using in module 5. If you remember the KSP or the relation to the saturated solutions too. Saturated means that they are now non-reactive, so they are quite happy with what the situation they're in. So if you look at the carbon to the hydrogen bondings, they're quite rigid, they're quite strong. So it requires some of the energies to break the bonds. So if we need to substitute that, let's say I want to substitute the hydrochloric acid. So it could be like HX, like this. Now, even the hydrochloric acid is quite strong, as in a strong acid, and chloride, if you remember the electronegativity of chloride, is pretty strong. It's stronger than hydrogen and the carbons, but it is not strong enough to break the bond between carbon and hydrogen. So we need help, some use of the catalyst to break the bond between the carbon to the hydrogen, which I'm targeting this. If I'm targeting that, we need help of the UV light a lot of times too. So what the UV light do is UV light comes along and it will break the bond between the UV light, because UV light is known as just light energy. which can break the bond between the carbon and hydrogen. If you just think about if you're exposed to UV light for a longer period of time under the sun, you may get the skin cancer. That's similarly, that's basically happening to like our bodies, and same thing happens to alkane structures too. So once that bonds are broken, then as you can imagine, the carbon to hydrogen, you can see like a highlighted one, they are ready to go. So it's broken now. So chloride, which is highly electronegative, will take a place of that broken bonding. So chloride will be attached like this. So I just pointed out what the different carbon number, carbon color here. This hydrogen and that hydrogen and this chloride and that chloride is now attached. So what happened now? We get the byproduct of the H2 or H2 is produced. But one hydrogen is from this hydrochloric acid, another hydrogen coming from that's the broken hydrogen's part. So remember that for the alkane, if you want to substitute something, we always need the help of the UV light, not only for the haloalkanes, for the hydrogen gases too. So that's basically what happened. Like if you want to get the alcohol from alkanes, we can go for the process from alkanes. Can you see like from alkanes to go through the substitution? You of must write it down of the HX. And then this goes on to the haloalkane, and the haloalkane goes through another substitution with the high sodium hydroxide or the strong base. I use a NaOH. Make sure I write it down. NaOH is used and UV light is used, and then we can produce the alcohol with what we want to make. The second method of producing alcohol from alkane is from the alkanes, we can go for the number 6 chemical reaction, which is hydrogenation. It's a type of the substitution reactions to move it on to the alkene, and from alkene go through the hydration process. So let's have a look at the number 6, which is the substitution to, also known as hydrogenation. The way you can think about hydrogen, the naming is hydro always stands for the hydrogen. Genation is like the adding or born of that too. So hydrogenation, it's actually going out of way. No, it's actually removal of that hydrogenation. Okay, no, alkenes to the alkenes, alkene to the alkynes. You know what? Let's forget about this hydrogenation. It's actually going other way around too. It's actually the arrow should go this direction. My bad. Okay, it should go to this direction, not the other directions like this. Okay, so let's talk about number 7 with addition reaction from the alkenes and the hydrogenations too from the alkenes. So just rewrite it over here like this. The method to produce the alcohols from alkene. So from alkenes, we can go for the halo alkane, and we can move it on to the alcohol. That's one method. Or we can do like alkenes to the alkane, to the haloalkane, to the alcohol too. So it's really more complex because it takes the more extra steps too. So let's talk about first this one, alkenes to the haloalkane methods. So that was the given number 6 hydrogenation process. Just write it down, number 6 reactions. Number 6, the hydrogenation is the process that we are having on alkene. So I'll show you the example of the alkene, which is ethene, as usual. This is going through the reaction with some H2 with the help of that. But hydrogen is not strong enough to break the bond, so we need a help to break the bond between the carbon to the carbon, specifically aiming that for carbon at the bottom. We need to have some acid, so H2SO4, to help the break the bonds between the carbons to the carbons. Well, time to time, we use these as simply a catalyst. That will be varied by like in what catalyst we use. Quickly have a look at the what catalyst we use for the hydrogenation process. Not this one. Hydrogenation, hydrogen. Oh, it's actually given here. We use the catalyst called the platinum or the nickel. It's the term we generally use to. So let's get rid of the K2SO4. Let's write it down. The platinum and the nickel, which is a common like a metal catalyst. And what does it do is it will opens up the bonding. So it will becomes like this. We have now changed the alkene double bond into the single bonds forms like that. So those hydrogen will be now attached to. So this is a type of the addition, the reaction, and also known as hydrogenation because we simply attach the hydrogen. Hydrogenate, something with genated means we are adding on to it. So from that hydrogenation, we now have our hydrogenations. Oh, I'm sorry, like I need a break. Okay, let's go to alkane process number 6. Is a common method from the alkane, then we can move it on to alkane to the haloalkanes, going through the substitution reactions and producing that into the alcohols too. Now, number 7 is the what I want to say from alkene. So from alkene to the haloalkanes, and that process is known as hydrohalogenation. It's a process that is called. So hydrohalogenation is basically we having one alkenes, and this go through the reaction with HX. So for example, hydrochloric acid, H bromide, HI, any of those halogens. And as HX is, and especially the halogen side is a really the highly electronegative, we don't need catalyst, so no catalyst required for this process. And it just simply opens up the double bonds and makes the attached or the adding those HX into it. So it makes it X will be now attached here like this forms too. So this is known as hydrohalogenations, whereas we're adding the hydrogen as well as halogen onto the double bond carbons. So just addition, the number 7 over here, I just added it as hydrohalogenations. Hydrohalogenation for that. And for this process, no catalyst required. Alkene to the alkane, we need to have the platinum and nickel is required. And now you can see there's some kind of roadmap to produce the alcohol from alkene to the alkane or the haloalkane to the alcohols too. These are general trends of the chemical reaction of the alkane and alkene as well too. Does it make sense?
Yeah, makes sense.
Okay, good. Now, another thing that we have to talk about is it's also known as bromine water experiment in between alkene and alkene. So showing you that alkene and alkene can go through the chemical reaction known as halogenation or dihalogenation to be specifically. So we can have something like this. We may have dihaloalkane. Consider what I mean by dihalo compared to just halogenation, dihaloalkane process. Now, dihaloalkane means that we have two halogens attached to the alkene. So from the process from the alkenes to dihaloalkane, we can go like this. There will be addition of, so what reaction now? Number 8, reaction of the addition of the X2. It simply can add the two. And this may be known as the dihalogenation or halogenations too, doesn't really matter. And no catalyst required for that process. But if you want to go from alkanes to the dihaloalkanes or like haloalkane process, so alkanes to that process here, alkanes, we go like this. Oh, sorry, different color. Go like that. That be known as the maybe some addition, same addition. of the X2. But that requires, again, the UV light of that too. So I show you the reaction between two. In the using the famous reactions of the bromine water experiment. So what reaction number is eight? Number eight is simply addition of X2 on the alkene. So famous example is cyclohexane. So cyclohexane look like this. We have six carbons joined together, and only one of the bonding is double bond forms like this. This is known as cyclohexene. And you can imagine, think about this, hydrogens kind of hidden. Show you that all the hydrogen structures if I need to. Goes in form like this. And you may see like there's a double bonds in here. What we try to do is we try to add some the BR2. And that could be a liquid, so if that's a pure bromine, but generally we're preparing the bromine water, which is made of all the aqueous status too. Now, what the bromine do, what does a bromine do is bromine is known as really strong electronegativity carrying properties, which means it is able to break the bond between the carbon to the carbon as well, so that it will come it up to like this. So I just highlight the bromine with the red like this, and it opens up the double bond and therefore producing attached onto this carbon, showing the carbon structure here again with the ring structure, we now have two bromines attached like that. Okay, can you see that these two are attached by breaking the bond between? And the hydrogen will be attached like in the other side of that too, just keep the hydrogens. And there will be no byproduct of that. So this is why we can also say it's an addition reaction of the alkenes. Then how do we know this will be produced? You can see from the something bromine water experiment, which will be, I can provide you data here. So it looked like this. So if you haven't done like a bromine water experiment in school, you probably can see like they'll be showing you some decolorization of that. So it is, it takes so long. Sorry, it takes a bit of time. Let's just show you the image. Yep. So it will be look like this. From that I can experiment, you may see like decolorization. So the colors of the cyclohexane is, it's good to know, it's colorless. By adding some bromine, which is a brown, the brown color, if there is no reaction, they'll be coming as the kind of pale brown, the brown color itself. But as we have a chemical reaction between the haloalkanes, sorry, the cyclohexane to the bromine water, we now have the colorless color will appear. So that's shown into this diagram here. Bromine water is decolorized due to the reaction between cyclohexane to that. We generally use a cyclohexane because cyclohexane is known to be more stable compared to other linear chain alkanes or alkane structures. So showing you that what happens to alkanes then, if we purely just have alkane, it would look like this. We have cyclohexane. So there is no double bond, so known as cyclohexane is given. And you can think about all the hydrogens is attached in here. Now, if we put that into the bromine water, remember the cyclohexane is also known as the colorless, the color. So when we put some bromine water plus the bromine Br2, which is the brown, as we adding some brown color into the colorless color of that, you'll be able to see that the colors will be changed into forming like into like this. Oops. It goes like there's a no reaction. Okay, so in real the colors will remain as a brown self without any like exchanges. Does that make sense?
Yep.
Yeah, but if you want to proceed the reaction with the bromine, maybe like substitution or the substitution reactions, this is what we can do. We can use in the help of the UV light. Remember that the purpose of putting the UV light always, UV light is the one that breaks the bond between carbon and hydrogens easily. So what does UV light do? It would break one of the bonding. So maybe like targeting this one. I don't know. Like it could be random. So it could be targeting this one over here. As a result of that, the bonding is broken. So now it becoming two cyclohexane structure with one bromines attached like that.
Is
If
the
we, hmm?
screen frozen?
Is the screen frozen?
Oh, there we
Is
go.
it better? Okay, sorry. Yeah. So no reaction part is shown by this part over here. Okay, so going back to the cyclohexane with the colorless and the brown color made it to. If there's no reaction without the UV light, there will be the colors of the brown will appeared. But in the help of the UV light, we're basically breaking the bond between carbon and hydrogen, as you can see that noted here. It'll break the bond, and if we extend the time of the showing the UV light on the samples too, sometimes UV light can break all the bondings of the hydrogens like this. So it really depends. So when we're showing the UV light, we actually show like sometimes like a certain time we're showing that to, maybe like goes like 10 seconds or 30 seconds, but we don't really expose to like, for like a day or two because we know that when the eye can get exposed to UV light for a long time, all the bondings between hydrogen and carbon will be broken down, which means there's a chance that the bromine will be replacing all the hydrogen bonds. Okay, so but as a result of the replacing one hydrogen here, the colors of the alkanes, cyclohexane, will also compete the colorless sp2. Now, the main difference between this and the chemical reaction 8, addition of the X2 to that, this is adding the 2 of the bromine. So the name would be dibromo, cyclohexane will be given. Compared to when we try to add some HX, which is a hydrogenation, hydrohalogenation, which a HX is attached to, which only has one X is attached. Compared to what we have in the dibromo, which is adding the X2, this is producing making the alkane with the two halogens attached, not just one. So it makes a huge difference between two. And we don't really use the cyclohexane or dibromo to produce the alcohol. So you can just understand that as the main difference between two. And another thing you need to know between cyclohexane is if you ever do like prac in schools, you're probably able to see um, things like this. So this is also commonly shown in the chemical reaction. So you may ever see like that this is a bit clear and just that's basically the cyclohexane. And we added it to with the bromine water. Okay, now, Yuri, why do you think we have a layers of the cycle like when we're adding some bromine to the cyclohexane? I mean you can see like the colors got disappeared compared to the one on the right, but what makes the layers from the top and the bottom?
Isn't the cyclohexene like so strongly bonded with carbon that the densities are different?
Good. Okay. Comparing to here, showing you the chemical the structure of the cyclohexane and dibromocyclohexane, which do you think has the greater density?
Um,
Comparing cyclohexane and dibromocyclohexane.
would it be cyclohexene?
Why?
Because double bonds double bonds like more like prioritized than like haloalkanes.
No, the double bond actually doesn't do anything. What we need to like consider here is the what type of the intermolecular forces they're carrying in that cyclohexane and dibromocyclohexane. What is the intermolecular force? Whether we have double bond, triple bond, I don't care. It doesn't really matter. But what would be the intermolecular force carried by the cyclohexane then?
Um, of dispersion forces.
Yeah, so there'll be dispersion force only. I mean, nothing else. No, there's no polar. Therefore, there's no polar intermolecular forces between them two. What about dibromocyclohexane?
Uh, would uh dipole.
Good. Dipole, dipole. Because it's always coming back to that. This is why I've been warning you from year 11, which you want. Guys, you will get it back again and again. And that's how we did make the question, the HSC and political exams too. As you know, dispersion force is much, much weaker, like intermolecular force and dipole-dipole interaction. So when we have the dibromocyclohexane with the full of dipole-dipoles, I'm expecting that the interaction between the dibromocyclohexane is much greater. So that means that they will be attracted towards to each other really strongly. So what happens to density if we have a really something bonded together strong? It will appear as the greater density as well too. Doesn't it make sense? Hello? Doesn't it make sense?
Yep, makes sense.
Yeah, yeah, yeah. And in terms of the cyclohexane, it's because it only carries dispersion force, it will have the lower this lower density will be appeared. So going back to the form here, the one that's submerged down, one at the bottom, is more dense compared to the one at the top. Okay, so the one at the bottom is then we can say should be dibromo, the cyclohexane, as is more higher density. And that must be the remainder of the some cyclohexene, which is low density values too. Remember that sometimes the question can ask you like why we have two layers of that too. Student just preparing like by memorizing what happens to colors. But examiners nowadays are giving the questions about, hey, why do we think we have a layers? And this is a good question because it's also asking about intermolecular forces all related. Okay, does that make sense here?
Yep.
Yeah, going back to the chemical reaction then too, we are done up to this part. There's a final method to produce the alcohol. Now, slightly different to the other two. We are using something known as the glucose. And you're probably familiar with this method because you did that in SRP in year 10, producing glucose to the alcohol. Any chance you know the name of the chemical reaction?
Uh, fermentation.
Fermentation. This is like actually known as a fermentation. Legit fermentation. Yeah, that fermentation. Yes, that fermentations. So what do we do for the fermentation process? Fermentation is using that process known. It's important to know what's involved in the fermentation, and if you can refer to your SRP in your tennis book too. We need to have some sort of yeast. I mean, glucose is basically sugar. So from the glucose, the yeast, and we put the yeast, and the system needs to be anaerobic. Anaerobic means that no oxygen required, so this is why we seal that whole structures. And the temperature, do you remember the temperature for your fermentation process?
No.
It's been a while. It's generally be 25 to 37 degrees Celsius. We try to perform that within like a room temperature, like a slightly higher temperature, close to the human body core temperature. And above that, yeast, which is an enzyme, would not be activated. Well, it's not sorry, not the enzyme, it's a fungi. So it will not be activated above the temperature or below the temperature. Now, how does it do? So let's write it down chemical reaction with the glucose and the fermentation process. Number 9. Oop, that's not that fermentation. For the fermentation is one thing, just one type of the fermentation we only have. We have a glucose, which is C6H12O6. And this needs to be in AQ always. If you remember, like, we don't really get the sugar, the powdered sugar, we dissolve into the water always to activate the enzymes. And what we do is we put it into the system with the yeast as the catalyst with the 25 to 37 degrees Celsius and anaerobic conditions too. Anaerobic, again, there's no oxygen, the lack of oxygen, O2. This is why we seal that. We don't really export to the outdoor. And as a result of that, we are producing C2H5OH and two of that, which is known as what? Then This is known as an ethanol will be produced. So fermentation process of the production of ethanol from the glucose is a process there too. Okay, the limitation for the fermentation. Unlike the other like type of the production of the alcohols, fermentation only produce one type of the alcohol, which is ethanol. It cannot produce propanol or like butanol. It will only produce ethanol due to that property of the glucose structures too. Another limitation is that it is not perfectly like making the ethanol 100%. So the amount of the ethanol we produce, amount of ethanol we can get from the fermentation process is relatively lower than other industrial processes too. But this is also very important that this is also known as biofuels. So if you ever heard about in petrol stations, the E10, have you seen that before?
Sometimes, yeah.
Yeah, okay. Like if you have a chance to go around, like it's like an E10, like you just have a look at the petrol station, it says over E10. This means the bioethanol, 10%. The bioethanol, which is the ethanol produced from the fermentation process from the glucose, so you basically use sugar cane or something, use the crops producing the ethanol, mix it into the fuels, because this glucose, this ethanol, it can also be known as sustainable and the renewable. Why is it renewable? What do we do for the CO2 produced? Once they combusted, we produce a lot of CO2. Now, if you remember the process called give me some ideas about this one. Process called the top of that, photosynthesis. Photosynthesis use this. We have the CO2, 6 of CO2 gas, reacting with the water, 6 of the H2O liquid, producing that in C6H12O6, which is the glucose here again too, and get the 6 of the oxygen. Now, what you can see there is the CO2, which was a byproduct of the fermentation process or the byproduct of the combustion of the ethanol, can be recycled, can be reused to form the glucose back into, and this can be recycled. This is why we say bioethanol is, or biofuels are renewable and sustainable compared to the other fossil fuels. Okay, this is also part of your syllabus point. Does that make sense to you, Yuri?
Yep.
Okay. Now, I think it's enough to talk about the production of the alcohol. So by next week, can you memorize all the alcohol reactions, the production of the alcohols? Then I will talk about the how to use the alcohol next week. So it'll be another hour session to the
Okay.
talk about the alcohol, like the how we use what alcohols you use. So I will save these files and I will share this video to you and share all the docs up to date. Do you want me to send a PDF of this?
Um,
Everything that
yeah, sure.
Yeah, yeah. I will share that to you and share the video link. I'll probably put it onto the YouTube or somewhere. So have a watch that. It's very important. And you all there are 9 chemical reactions we discussed it today. Oh, it's actually 10. I forgot there's a 9 on the top, so let's write it 10. It should be 10 fermentation reactions. So memorize the 10 chemical reactions till up to next week.
Okay.
There'll be about 10 more coming next week then.
10 more.
10 more.
Okay.
Yeah, this is a requirement. And yeah, that's fine. Try to just, okay, what I recommend, try to memorize that as some kind of flow chart of the chemical reaction, as I did on my, like over here. So if you have an A4 paper, the blank A4 papers, try to like memorize by understand the draw the flow chart of each of the chemical reactions and provide some details like this, like these summary notes get provided here, rather than you try to just read that and memorize it. I don't think that would be helpful to memorize them.
Okay.
Okay. All right. That's all for today. I will talk about this more in next week then.
Thank you.
Okay. Bye.